All right, so in the last video, we talked about the derivative and what it means. We went over a couple of really simple examples of calculating the derivative. Here we're going to give two more examples that are a bit more complicated in how we calculate the derivative. So let's go ahead and start. So what we got right here is we got an equation of a line, y equals x squared plus 1. What is dy dx? Remember, dy dx is just another fancy way of saying the derivative, okay? So why don't you guys yourself try to use the difference quotient to calculate that derivative right there. Pause the video, see if you can do it on your own, and then we'll see what you get. All right, so if you went through and tried to do this, the first thing you should have done was plug everything into the difference quotient equation. If you did it, it would look something like this. Again, this section right here would be f of x plus h. This one right here would be f of x, remembering that difference quotient equation. Okay, so if you go through and do that and you simplify a little bit more, you'll get something that looks like this. So what's some of the magic that happens with this? Well, we have an x squared right here and a negative x squared. Those two cancel. We have a 1 and a negative 1, and those also cancel. So if we continued, we would get something that looks like this. All right. So if we get that guy right there, let me scroll this up here real quick. Yeah. All right, so if we end up with that guy right there, well, what do you notice happens? Okay, well, when we get to this step right there, each term has an h, so we can factor the h's out. Once we do that, we'll get an h in the top and an h in the bottom, so those cancel. Now we are left with a limit that we can actually solve. If we plug in h equals 0, we're just left with 2x. Now notice that before this step right here, if we tried to plug in h equals 0 to this limit here, to this limit here, to this limit here, or to this one right here, we would have gotten 0 over 0, which was indeterminate. So we had to go through all of these steps to calculate it this way. All right. Now, while unlike in the previous video, we needed to use math to calculate the derivative right here, we actually could have conceptually understood the shape of the derivative without actually calculating it. I'll show you how. So if we look at the function y equals x squared plus 1, that looks something like that. So let's just let's look at, I'll use a different color pen for this. Let's use red. So let's look at the slope of the tangent line. Remember, the derivative is a function that gives us the slope of the tangent line to the curve, or the instantaneous rate of change of that curve at any given point. So let's say we were going to look at an x value right around here, okay? Well, if we go up there and we go up to our function, we're going to get a tangent line that looks something like that. All right, so what does that tangent line look like to you? Does it look steep or shallow? Well, to me, that looks kind of steep. Does it look positive or negative? Well, that's negative, all right? So at that x value, we're going to have a fairly big steep slope. So then, let's erase this one. If we are going to, let's say, look at another x value a little bit closer, well, let's look at that tangent line. Okay, that tangent line right there is going to look something like that. So again, that's a negative slope, okay, so it's going to be negative, but is it more steep or less steep than before? Well, I would say that's less steep. So, therefore, at that x value, we're going to have something that goes like this, okay? Now, what if we look at x equals 0? Well, the tangent line right there would look basically flat. We would call that a horizontal tangent, okay? And what's the slope of a horizontal line? The slope is 0. Hopefully, you're kind of seeing the pattern that's coming right here. And that if we were going to continue to do this, we could actually find what the derivative function would look like just by analyzing the slope of the line tangent to the curve x squared plus 1 at any given point. In the next video, we will specifically look at how we graph derivatives based on their functions. Okay? So now let's go to another example. All right. So this one is a bit more conceptual in nature. All right, but give it a shot, see what you can do. Try to answer this one, all right? Try to pause the video and see if you can answer it on your own. All right, so if you tried this one, you'll notice that there's a couple changes that we've made, all right? First of all, we've changed our independent variable from x to t. All right, so now instead of having x on the x-axis, we have t. Now this changes nothing in the math that we're doing. An independent variable is simply an independent variable. We could have on the x-axis like a dollar sign if we wanted to. We could have a smiley face if we wanted to. Okay, it doesn't matter. It's just a symbol. That's a pretty terrible looking smiley. Well, maybe it's a side profile, so you know they're looking like in that direction. Okay, anyway, but so the fact that we're using t is really just convenient to the problem. When we talk about position, velocity, acceleration, time is always going to be our independent variable, so that's why we use t, but it doesn't change the math that we use, okay? Again, remember that what is the relationship between acceleration and velocity? Well, acceleration is the rate of change of velocity. More specifically, acceleration is the instantaneous rate of change of velocity. So therefore, if we're asking for what is the acceleration, we're saying what is the derivative of the function v of t. So the first step you should have come to was plugging everything into the difference quotient, okay? Right here, this says what I just described about the relationship between position and velocity. This says that acceleration is the derivative of velocity, okay? That's in math speak, that's what that is. And this right here is we're just plugging everything into the difference quotient, okay? That's just direct application of the difference quotient. So once we actually solve for v of t plus h and v of t, we're going to get a limit that looks something like this. All right? So now that we got that limit, how are we going to simplify that? Okay, well, you see we got two different fractions or two different quotients in the top. Do they have the same denominator? No, they don't. So if they don't have the same denominator, what must you do to add them together, or in this case, subtract them? You got to find the lowest common denominator. And in this case, the lowest common denominator comes from multiplying both denominators together. So if you go through that and do that, you will end up with this limit right here. Okay? Now again, let's look at this. What magic happens? Okay? Well, you'll notice in this top right here, we have a t and a negative t, so those will both go away. And then when we distribute the negative sign once more, what we'll get will be that. Okay? So what do you notice? In the top and the bottom, we have an h and an h. So those go away. If we do that and cancel those out, we'll get this. If we plug in h equals 0 into this limit, this term will go away, and we'll just be left with negative 1 over t squared, and that will be our acceleration function. Okay? If you couldn't do this one, go back and try it from the beginning and just try to do it again. It's really good practice. Now, as with the last example, remember that we can get a conceptual understanding of a derivative based upon the original function. So if the original function is 1 over t, well, 1 over t looks something like this. So why don't you ask yourself, okay, when we're at really low x values right here, what does the slope look like? Okay, the slope tangent to this curve at x values down here, that's the line tangent to the curve. That's a pretty steep slope, and it's negative. And the closer we get to x equals 0, so the closer we are going in this direction to the y-axis, the steeper that slope is going to get. So therefore, if we plot the derivative, we start with a very steep negative slope as we get closer to 0, and a slope that gets less steep and less steep as we keep going along. Now eventually, if we get to say an x value around here, our tangent line is still going to be negative, but it's not going to be nearly as steep, okay? That's why the derivative curve is moving closer to 0, but it's never going to actually hit 0. What we have right here is in this function we have a horizontal asymptote on the x-axis. So our slope of our tangent line is always going to be negative, but it's going to get smaller and smaller and smaller negative until it gets really close to 0. So we will never actually end up touching this t-axis on the a of t function right here. However, go in Desmos, plot negative 1 over x squared, and it will look something like that. Now it'll have an opposite side that goes like this. Why do we not have that in this problem? We don't have that because we said t is greater than 0, okay? So we don't have to worry about that side. So again, next video, we're going to be focusing a lot more into how we graph derivatives based upon what the original functions are.